Okay, so we have about 45 minutes planned for the presentation itself, maybe a little bit less, and then we will have 15 minutes of questions and answers. You will be able to post your questions here on the right, and I'm not giving people microphones because in such a big audience, usually microphones are a bit of a problem. I have my partner and colleague here with me. His name is Suji Maniyam. He may be able to speak. And I also have our sales director, that's David Kaufman. Other than that, this is the presentation about machine learning, and what you are looking at is Adobe Connect. We actually also teach machine learning, and that is the medium that we use. We usually use this online meeting anytime that we teach, whether it is remote or whether it is in class. So you are able to see your slides. You are able to see who else is in that meeting. You're able to take a quick poll, to do questions and answers, and you can also chat. You can even spend your time chatting to each other. Just right-click private chat. You can do such things. So it is a powerful media, and that's why we prefer it. And the subject today is everything you wanted to know about machine learning, but machine learning is confusing, so you couldn't really find a good place to ask. I hope that will be that place where you will be able to also ask your questions. Here's what we want to touch upon. We want to, in the end, not on the very first thing, but in the end, we want to see how can I start using this machine learning right away. That is the low-hanging fruit. We want to show you how machine learning is different because it is on the one hand deep science, on the other hand it is a fad. So we want to know how to combine them and how to build your team accordingly to the maximum success. And we also will talk about which particular tool you might want to use. There are many of them. They are all good and they all have their positive sides. So we will talk about this. Now, in the class, we usually say that in order to follow the class and the labs, you need to know this. For our presentation here, you do not. We're not going to give you the labs. We will just give an overview of what this machine learning is. So you don't have to be that technical. We will go above that. That would be for the real class. The way to teach is teach how to do. Sometimes people don't know where to start. So usually when you want to go deep into machine learning, you want a lot of labs, you want a lot of actual to do things, and sometimes you don't know where to start. So in that case, we actually tell people that's where you start. We give them the environment on our Amazon Labs. But in the end, hard work pays off, and you can claim that now you know that machine learning, not a big deal. You've been there, you've done that. There is so much that you can cover, whether it is a 3-day course or whether it is a 1-hour webinar. This is a list of the few books that I found to be the best. The very first one talks about how exactly use Spark in general and machine learning in particular. The second one concentrates more on other languages. The first book was with Scala. The second book is more with Python, and it's more on a very practical side. And this book on the right is on a very theoretical side, so that way you achieve a complete mix. And I will show you exactly how that theory meets that practice. So why would you want to talk about machine learning in general, other than that, if you Google on machine learning, you will probably find 4 billion results. The answer is that it became very popular, and it's the results that it gives, yes, but it is also the timing is right. We'll talk about that. First of all, what does it give you? Credit card fraud prevention. I think everybody here is familiar with that. I'm not even making it a poll because I'm sure that everybody has a credit card, and with that credit card comes credit fraud. The fraud is different in different countries by level and also by protection. But in any case, all of the major credit cards are working on the technology that will help detect the fraud. So you could have thousands of different transactions that's going on, thousands of features and billions of transactions. How do you find out something that's completely out of the ordinary? If you travel somewhere, you shouldn't be stopped. It's normal. So that's not a good sign. If you suddenly shop for a $1 item in a remote stop and go store, then maybe that's the wrong thing. At least I was stopped on that once. And you should be able to confirm. All of that is done with the machine learning, and more specifically, you can do it with an algorithm called classification. More specifically, SVM, support vector machines classifications. So you see how you start with the practical problem and then go into the algorithm that actually does it for you. That is why we outline what the use cases are, but then we also go into the depth of the technology. The next popular application of machine learning today is recommendations. Everybody sees them all over, and Amazon used to be a literary review site before it became mostly a recommendation site. Another example is that Netflix gets 70% of the repeat business from recommendations. So how do I make precise recommendations is a huge art because it's very easy to make a wrong recommendation and turn a person off. Financial risks. That became possible today with big data to estimate very precisely, and that is one of the machine learning tools that people do. They simulate the portfolios and then they do what if analysis. The difference is that they now go by minute transaction, not by monthly averages. And another good example is genome data manipulation. There are big projects about this, and they all use machine learning as well. So these are the tangible benefits and these are the results. Now, how do you get to them? The way to get to them is by using one of the platforms. There are multiple platforms. The one I'm concentrating upon right now is Spark. So let's do that first. Later on, you will be able to ask questions about possibly other platforms. So what is this Spark? Spark is the next generation of Hadoop, you may call it that way. It gives you manipulation on big data at scale and in real time. You can be in an interactive shell and you can be doing your manipulations with the data. So these are the great things about Spark that I list here, but let me quickly tell you the story of Spark. It's aside, it's not crucial, but it's a very interesting story. The story is that Spark was actually invented at Microsoft. Microsoft wanted that to be a Hadoop killer, and they almost succeeded. They called it Dryad. Dryad was a great thing. The unfortunate for Microsoft's fact is that they killed it before it killed Hadoop. Then the people at Berkeley Lab picked it up and they made it with a few differences. They made it a great product, which can eventually kill Hadoop or complement Hadoop. That's the way you look at it. So that Spark is an execution engine. That really is what it is, and it speeds things up by putting them into memory. Right away, you will probably see why it's so great. Because in Spark, you will be able to play with your data and you will be able to play with your model. So you can try any model and right away see the results. If the data is big, you'll see it after a minute or two. Well, sometimes you have to train your model for a couple of days, even that. Still, it's the fastest possible environment. Specifically, our course concentrates on Scala, but that I would not say that it is a requirement because later on I'll tell you why you would not want to use Scala. If you do want to use Scala, the reason is because Spark itself is written in Scala, so it's a good way to learn to think in Scala, and Spark gets all the novelties in Scala first and other languages last. But why would you want to use something else? It's because you may like other tools. Python is a great language, it's very well known and has many packages that Scala right now may be missing. One of them is graphing. There is nothing to visualize your data in Scala today, but Python has visualization. R is even more popular in the sense that it's gaining popularity since it has a lot to gain, so R is gaining it probably faster than other languages. So it's your choice, whatever you would want to use. Now, What is this machine learning? Let's go into, we saw the benefits, we saw the platform, we saw the languages. What is it exactly? It is an algorithm that learns from data. It can learn from data in a few different ways, but in every way what is important is that instead of telling the data what to do, such as I sell something and I take that transaction and store it in a database, I ask questions from my data. I'm asking, tell me please, what is the most popular product? Or tell me please, what should I concentrate on in the next quarter? That is learning from the data. And it is a mix, I would call it a hodgepodge of different methods. Now, a little aside that's not here in the slide. The machine learning as a term is pretty old, but data science, and that's what you will see as a very popular uh, moniker for that, was invented by Jeff Radenbacher when he was working at Hammerbacher, when he was working at Facebook. That became extremely popular. It's considered one of the sexiest professions for the next 10 years by the Google Chief of Human Resources. So that's why people have questions about machine learning. It's a combination of some methods that were invented a while back but grew popular today, plus some methods that were invented in the 50s or 60s, plus some of the newest things that were invented perhaps maybe a month ago. Let's look at it in more detail. If we look a little bit at history and we look what happened in the 60s from the data science or machine learning point of view, then we know that they already had AI. They had artificial intelligence, and computers could play chess reasonably well. Then in the 80s, they grew in love with this computational complexity theory. They wanted to know, is it possible to compute something or is it not possible to compute something? And one of the books that I recommend talks about this. This is where artificial intelligence grew in popularity and then suddenly fell out of favor because it overpromised. So for a while, you couldn't even mention the word artificial intelligence without being considered somewhat of a bad name. And it's all coming back, as you can see, it's all coming back a little slow at first. People were using these same methods, but they were not calling them AI. And then suddenly things changed with the big data. So I'll show you how they changed with the big data. One of the interesting questions that they ask in computational complexity theory is this. If I have a problem, and if I can verify that I got a solution and that solution is right, does it mean that I can also solve that problem? So let me repeat that question. If I have a problem and I know how to verify that a given solution is correct, does it mean that now I can find the solution that somebody previously somehow gave to me? Theoretically, if I have unlimited time and unlimited resources, I can go through all of the solutions, and since I now know how to verify each solution, then theoretically the answer should be yes. Well, practically it's not yes, because I cannot afford to go through all of the solutions. And easy computation will show you that I'll have to go, in many cases, through more combinations than there are particles in the whole universe. So that question by itself is left unresolved. But really, by now it doesn't matter. And here's why it doesn't matter, at least not as much. So that's a computation that shows you how you can very quickly get into very big numbers. Okay? The reason that doesn't matter is because in big data, you don't really solve the problem. You rather find that answer created by somebody else, or you find the best close answer. And you're not really spending time on creating the best possible solution, but very often you're finding it by automating humongous search on Google. So the new approach is not just solving the problem, but using the existing human and machine intelligence to parse through the solutions. That's one of the reasons why it's not that important, is the problem solvable or no, as long as I have a practical algorithm. Another reason is that with big data, you grow out of one computer. If we go back into the 80s when the complexity was popular, they were all thinking about one computer. But one computer has a very practical limit, as much hardware as you can put into that. So you hit that limit much faster than you hit the computational limit. Therefore, today, our practical question is, can I solve it on the cluster that I have? Let's say I have a 100 machine cluster. Can I solve that problem? A very practical question. That's how the new data changes it all, and that is how you have a different approach. Let's look at, let's say, machine translation. In an initial effort was by IBM, and they combined all of the best possible answers for translations from about 5 million answers. Because they felt data should be very clean. Google went the other way. They combine all of the data in the world and they have all of the possible translations mixed, and then they select the best. And 100 billion words is what you really need. So here are the lessons. We can use the world data and we can arrive to great solutions as long as we have those methods. By the way IBM, Dr. Watson, who won absolutely the Jeopardy contest against the best human players, used the crawling of the Wikipedia. So there you are. You don't have to understand too deeply if you can use the existing resources. Okay, very good. Now, the other extreme of developers is that developers don't think. They just develop. That we want to avoid. So we don't want to be too theoretical. We don't want to be extremely practical. We rather want to be somewhere in the middle. And I'll try to be exactly this in this webinar because I want you to show what is the problem, what is the solution, and what are the limitations. Okay, very good. Now let's take a look at specifically machine learning. You probably already know that machine learning means that you're given some data, and in this data you're telling, well, humans have found that this data means that. For example, let's take an example that is familiar to me. Let us say you are a team of lawyers working on a certain case and you're doing a legal review. Well, it's not as hard as it seems. If you ask a few lawyers to find a few examples of the documents that are important as opposed to documents that are not important, and then you label these documents as important, not important, and then you give it back to the machine, it can extrapolate. It can say, I see these factors that led to documents being important or not important, and I'm going to classify all of the other documents based on that. So in that example, we have the classical example of model being trained by humans who applied labels to that, and then the model was applied. How good or how bad is that? Well, that depends on the people who selected the labels. So first of all, you need to make sure that your labels are good. When we are talking about the latest efforts, I will show you how people ensure that the labels are good by using extremely big amount of people who are doing the reviews. That would be supervised machine learning. It's as good as the data that you feed it, and it's also as good as the model that you find. Not necessarily you will right away find the model that really reflects the meaning. The next one is unsupervised learning, which is in some sense better because you do not need humans to go through the data set before you do it. For example, clustering. When we look at, let's say, points, we very naturally cluster them into little groups, clusters of clouds. And that can be very readily applied to a lot of things. For example, I can cluster into some news items into groups of medical, health, entertainment, sports, and politics. So that would be a great way to help humans. Or I can cluster in just two clusters, fraudulent, not fraudulent. Therefore, these methods depend less on the human input and more on the methodology. And very often people use a combination of the two. You won't be surprised that in machine learning you'll have to go nitty-gritty into the detail, nitty-gritty into the algorithms, understand them and their limitations. The same applies to the data, and the same applies to computational power that you will have. All right, given that we have supervised machine learning, which is very frequent, then we'll have to use the usual approach. We divide our data into training and test. Let's say I divide my data into 70% for training. So that will give me exactly how many, which documents are, let's say, good, which, let's say, bad, and then my training model will be able to tell back exactly, precise, close to exactly the same results as what was in training. Now I will apply it to the test part of my data to verify the results, because if I really got the trend, then the trend should continue and the test should show me pretty high degree of compliance, just as in the training. That won't always be the case. There are multiple considerations here. Some people may overtrain by taking too little for training, too much for test. What I've seen in the latest Facebook work, for example, they use 90% for training, sometimes 95% for training, and only 5 for the test. But they have a huge amount of data to work with. So you train the model, and then you simply predict the result. When everything is packaged, for example, if you're actually now implementing machine learning algorithms in Spark, maybe in Scala, then all you have to do is to give the model the data and call one simple method. Since other people have done the work for you, you create your solution with just 2-3 lines of code, which is nice. But imagine how much understanding should go in the back, because you can write a wrong solution just as easily as the correct one. After you have done that, you can compare how was I doing, how is the predicted comparing to actual, and you will be able to see if your model is correct. If it's not, you'll have to try to see what is important about your data. Maybe it was the wrong model. Now, if we're talking about machine learning in Spark, then here are all of the methods. I will go through them in a bit in more detail in the remaining slides. However, all the slides will be available. They will be posted, so you will be able to look at that. Basically, we can say that it touches on every aspect of machine learning, and in particular, in the big data area, we have two libraries. You have Hadoop and you have Spark. So in Hadoop world, the machine learning is called Mahout, which means animal trainer, the elephant trainer. In Spark, it's called ML-lib, and today there is a new version called ML, just machine learning. So the telling fact is that the group of people who was working on Mahout stopped contributing to Mahout, and they are all contributing to ML, which tells you that you cannot go very wrong with the choice of Spark. I'm not trying to sell Spark, but it's one of the very good libraries. That's not the only one. We will talk about deep learning just a while later, and you will see that Spark doesn't have as much of deep learning as others as yet. Well, let's continue. So we have done our model building, we have done our validation, and now with this new and shiny model, we can go and predict fraud, we can predict failures, we can predict, for example, actual project I'm working on. We can predict a person who is in the hospital, and unfortunately, he is nearing the end of his days. So today there is a very, very popular idea of stop fighting and let him live a good life at the end. It's called a hospice. There is machine learning that allows you to find out who really should be doing this and who should not. There are other much more joyful occasions too, of course. You can sort out the hackers from your network, and you can do all kinds of things. Now, practically, you work with numbers. So even if you have something that's not a number, you need to convert that to numbers. Sometimes that's easy. let's say we're dealing with colors. Colors have a specific frequency. If we're dealing with texts, that's not exactly easy, and so then you need to apply some of the mathematical formulas that will allow you to convert texts to numbers. That's doable though. Then in particular in Spark, there are dense vectors and sparse vectors. That's something to deal with efficiency. If you use the wrong one, it will still work, just not as fast. And that applies actually to many other languages. If we're dealing with text, then the easiest to understand measure is TF-IDF. I'll tell you what that is just as an example of what you do. Let us say I have 1,000 documents and I'm looking for a specific document talking about, let's say, hacking. So if I find the word hacking mentioned 3 times in the document, that's something. But what about other documents? How many times is the word hacking mentioned there? If it is just once, then this document is important. If it is the same 3, then it's not important. This is what TF-IDF does. It takes the term frequency in that document and divides it by the term frequency in all of the other documents. That way, you will arrive to one number, just one number. Of course, that's a very weak measure. There are many more algorithms that will allow you to convert your text into a bunch of numbers because you want at least a few dozen numbers describing each word. With the new popular word-to-vector algorithmization, they convert words in the context. For example, fox jumped is one thing, but fox and then who knows what and then not jumped is a different thing. The TF and IDF will not catch it. Word-to-vector computes those numbers within the context, and that creates about 400 to 500 numbers attached to each word. So now you're dealing with the 400 dimensional vectors. These go then into the machine learning algorithms. The results are useful. So that's a very simple word diagram, but you can go much more, much deeper in understanding, and we're coming to those examples. What is deep learning? Now, please notice that our webinar is specifically about machine learning. Deep learning is not really machine learning. I'll tell you what the differences are. Machine learning, even though it sounds all-encompassing, but it really means those algorithms that are essentially fitting my model to the data. So for example, if I think that my model is linear, let's say I'm looking at the prices of the houses, and I feel that a model is linear and the prices go up as years go by, then that's machine learning. Deep learning is something else. It's very specifically something based on neural network. And more specifically, if we have a neural network that has more than one internal hidden layer, this is called deep learning. Deep learning became very popular in the last year or two, I would say. So let us touch on that, understanding that deep learning really deserves its own individual course and its own individual, let's say, webinar. So in neural networks, you're trying to act pretty much like the human brain does. And here is how it works. It is stimulated by all other neurons. You have your brain, and the brain cells pass messages using, by the way, chemical, not electrical signals. And there you are. That's the model that you use. So you have multiple inputs multiplied or maybe divided by some numbers, and finally it's either yes or no. Well, it seems very simple. Yes, it is. It begins to show its power when you have multiple layers, not one, and multiple data sets. For example, here is a deep neural network that understands faces, and here is deep neural network that understands texts. So here I will just briefly describe the latest results. You can look them up. Google understands text and translates actually pretty good. You can look at Translate Google, and the technology that stands behind it is this. word to vector. And Facebook, their latest achievements was described in an article just 3 months ago, and they understand text from scratch by taking letters as the input and getting the meaning as the output. So that's a tremendously groundbreaking approach because it doesn't depend on the language any longer. You can feed it any language. You can feed it Chinese by using the spelling, the pinyin spelling, and it will still understand it. They productized it. They give it as a engine to the people, to the engineers at Facebook. And one interesting thing I wanted to point out here is that that article was written a few months ago, but the basics was done in 98. So you see that sometimes you have very old technology, but suddenly it becomes actually workable when you put it into the big data environment. That's exactly this example. Now, ML Live doesn't have that as yet. For that, you would go some with Google Tensors or maybe with IBM Deep Blue, but that's not what we're talking about. We're talking about machine learning, and machine learning is well represented in Spark. Now, we have a few minutes to talk about specific algorithms. So the first group is called the linear algorithms. They all assume that the combination of what is called predictors, that what goes into the algorithm. So let's give one example. Let's say we are a major telecommunications company and we're watching how people switch their channels. And we're watching millions of people, billions of switches. And we want to find out what makes a program popular. So if we assume that each of these factors, for example, how long did they watch the previous program, or what do they usually do, or the time of the day, or whatever it is a separate factor, then we call them a predictor, and they become our linear entries into the algorithm. So in that case, practically we were working with 8,000 predictors. And you assume that, not always correctly, but the wonderful thing is that it works anyway, that they are independent. So here's an example of a specific linear method, but it's a linear method called SVM, support vector machine. Here's what it was originally used for. Let's say I have observed a tumor, and I know this is the size and this is the progress in time. What's the chance that it is malignant? So that's exactly the method that will separate the benign tumors from malignant ones, and that's where it was developed. In the same way, we can use that same method for, is that a hacker attack or is it not? Is it a fraudulent transaction or is it not? As an example of who developed that, that's called logistic regression, was developed by a mathematician, became very popular today, even though the work happened about 20, 30 years ago. So that goes for all of the methods. You'll have to learn them, and you'll have to realize that some of the theory may be complex, that they have condensed it by creating the solution, and that maybe it was there for quite a while, but really became popular nowadays. That's why some people don't quite understand what this machine learning is about. Now we're getting it is a synthetic discipline that draws on multiple sources, but find its big uses in the big data and the cluster world. Let's look at classifiers. For example, the naive Bayes classifier. Where would that fit in? What is it? Naive Bayes is very popular for spam, email spam filtering. And the way it works is by saying, well, let's say I have free Viagra. Or Viagra maybe. So if I see these words separately, that tells me that it may be spam. Well, if I see them together, it may be spam as well. The problem is that really they usually do go together. So they're not independent. Our assumption in naive Bayes is that they are independent, not because it's true, but because it's easier that way. Well, and if we do apply it this way, then we can create an effective spam filter. So the amazing thing is those spam filters work even though the assumption is not exactly true. Another popular classifier is k-means, where you break it all into a set of clusters that's based on geometry, something completely different. The base classifier is based on statistics. And these two together give you pretty decent and good classifiers. They don't go, again, nothing goes as deep learning, but deep learning has been around for just maybe a year. As I mentioned, the books are just coming out, and lots of companies are beginning to use it. Machine learning is much more established, and I would explore what it can do before you go into deep learning, which is more specific, requires much more resources, at least computational resources, and also understanding. So that's how far the history of Bayes itself goes. It's in the 1750s. And then lately it's become popular, and they started using it in the 50s, just applying that formula to the data. Here are the use cases for that. I mentioned intrusion attacks, but you could use it for finding problems on the servers, problems on any sensors, clustering will not necessarily detect exactly what you're looking for, but it will flag them out, and you will then look at them for future investigation. Okay. Now, one interesting thing that it does is this. People like to talk about known unknowns and unknown unknowns. So, for example, for network intrusion, the known unknowns is port scanning, and there are many networks that simply block you on port scan or by the number of access. But the unknown unknowns are something we don't know what to look for. So what if it is a new and unclassified attack? What if it is a longer thread of emails? And that's where automatic classifiers also are useful, because they can detect something that has never been seen so far. They can say, well, that just doesn't fit the regular pattern, traffic pattern, even though I don't understand what it was, and then we can investigate it. That's where the classifiers come in. Finally, the last method I want to show is the optimizations. Now, optimizations are a completely different area. They were developed, especially this kind we're looking at, helping the mouse to find its cheese. That has been developed at the British mathematical labs during the war. They were using it to fight the Germans. It was then unclassified in 48 and published. And so it goes into the graph of machine learning. It goes into the optimization of machine learning. And again, let's have one big umbrella where we'll combine all the useful algorithms, and that's one of them. In that particular case, it is already implemented for you, so you will not have to rewrite your dynamic programming algorithm, but Pragiel algorithm in Spark will tell you exactly what the result will be and how a mouse can get its cheese. Okay, so useful for everybody, for humans, for animals too. Now, as I mentioned, that that webinar is actually based on our own deep study of what people do, plus our own work on this. So we have a bunch of courses that we teach. Here they all are. If you're interested, we have one of the classes that's already guaranteed to run. There are enough people that have signed up there, and you can see it at the bottom left in red. But that is not the major point. The major point is I hope I was able to give you the outline of what this machine learning is, why people talk about this, what it takes to get into that, mostly lots of work, some amount of computing power, and some training. And now it's good time to do the questions and answers. You can ask your questions here on the chat, and you can also ask them on the Q&A. So you're welcome. I can also prepare while you're doing this. I'll do a little poll.
Mark, I have a couple of questions posting on the Q&A panel, please.
Yes, I see the first question there. How about Spark and Python? That is a question from Rick. Okay, great. Uh, Spark comes with 4 languages out of the box. You can use Scala, Python, R, and Java. Java is one language I probably would not use because it's just a repetition of everything you have already done in other languages, just longer. But Python, R, and Scala are all very powerful contenders, and that simply depends on which language you're mostly familiar with. So if you are asking that question, I would say that uh, yes, go ahead. Python is completely implemented. On some of the latest things, maybe it will be a little while, like 2-3 months, before Python gets something that's already in Scala, but not in Spark, not in Python. But that's not such a big deal. And the last thing is that performance. Out of the box, if you don't do anything, then Python will be 10 times slower than Scala. However, there are ways to speed that up. So when you're doing your Spark in Python, then don't forget, look up how do I make Python well performing and match it to do what Scala does. Okay, the next question. I use R now. Should I consider Spark next? I would say definitely yes, because the way R works under Spark is pretty much the same as R on the command line. It's just a couple things where you're saying, well, before my R interpreter was reading all of the data into memory. Now it's reading all of the data into the memory of the whole cluster. There is more to it, how exactly that's being done, but I'm sure you know if you work in R that your memory is your limitation. You might be on a company server, maybe they give you 2 gigabytes of RAM, maybe they give you more, but in any case, there is much less than what you can get with the cluster. One of the biggest clusters I've seen, it has 43 terabytes of RAM. So with that, you could probably do any problem. So the answer is definitely yes. R is a popular and upcoming language, and R with Spark, well, now you're holding your big data objects. I'm preparing, while you're asking, I'm preparing my own questionnaire to you.
And Mark, we have more questions being put.
Mhm. One second, let me see your question. Question from David. I'm a software engineer. How approachable are the ML algorithms in Spark? Do I need to go learn ML? Unfortunately, yes. I'm meaning that I actually like to learn, but for people who are not into this, they would have a problem. I won't say it's extremely easy because you need to understand. But the good part is that it's already implemented. So once you grasp the model and you grasp how to prepare the data, then yes, you can go and do ML. You would have to learn it. So you can take a course, you can take a remote course or buy a book. You absolutely need to do practical labs or practical exercises. Otherwise, especially that part of theory doesn't stick. The next question from To. To. Do you need Hadoop to work with Spark? And what is the minimal configuration to start? So you don't, strictly speaking, need Hadoop. Many people today, um, they just bypass Hadoop. There are 40% of all Spark installs in the world that install Spark without Hadoop. That really is happening now. It does help to know big data or Hadoop because that is the background. So usually I teach people Hadoop first, Spark next, but sometimes they already have that background. So it's helpful but you wouldn't have to go into all the depth of Hadoop when you touch it. Just get the general knowledge, and then you can go and do Spark. The minimal configuration on Spark is here you're in the luck, because unlike Hadoop, which required you a real cluster or at least a virtual machine, Spark doesn't even want that. You can install it by simply unzipping, and that works on Linux right out of the box, and on Mac and on Windows with a few little hacks. But in any case, you can start learning about Spark right there on your laptop or desktop. Going further, you would need a cluster because you're going to work with the real data. The next question. What is the best way to run Spark on my laptop? And the same both Mac and Windows. That I already answered, but let me repeat quickly that you just download that and ask me a question, okay? Because on Windows there's a little hack that you need. I found it on one of the blogs and I teach it during my class. But if you have problems with that, just ask me. I'll show you what you need to do. On Mac, should work out of the box, even though I have seen people having trouble. But give it a try. It should really work. Okay, the next question is from Geoff Rothman. Have you seen any SaaS ML predictive apps that have an easy to use front end and use Spark ML in the background for processing? Well, that's a good question. I have been working as part of a startup that was developing exactly that. They use Spark in the back end because they could predict portfolio what-if questions in a reasonable time. Let's say Hadoop would take maybe 2 minutes to answer, maybe more. Spark could do it in a few seconds. That was reasonable. You show the person a wait cursor and he waits at the browser. So yes, I've seen them, but I have not seen them all that much out in the world, except maybe for HANA. SAP HANA has some of the sales analytics, and that really works in real time with the visualization. So that would be a good example. And people are working on that actively because that's exactly where the modern trend is. Everything should be very fast, ideally in real time. So the answer is yes, it's just coming, and I saw some examples, and please look for more because people are working on them. I see a new question. From guest. Is Spark still bleeding edge? We are a Hadoop shop. Should we consider Spark? Well, my own personal opinion, because I'm not the one to decide, but Spark is still a bleeding edge. Now, if there was something beyond that, and if you wanted to say that even Spark is not a bleeding edge, but there is something that is a bleeding edge, then maybe yes, but I don't think there is anything. Spark is about 5 times more popular than Hadoop if you judge by how many developers there are contributing to Spark. And I don't know of any other project that has that much of a weight behind it. Like IBM is all on Spark and so on. You can look at other machine learning engines, for example, Google TensorFlow. You can look at that, but that's probably not your question, because if you're asking about where on Hadoop should we consider Spark, then I would say definitely yes. That is the trend. All people that I know who either do Hadoop or when they learn Hadoop, they immediately ask the question, do I also need Spark? Some of them even say, well, stop that Hadoop, let's do Spark. That's a bit an overkill, but I would definitely say my opinion is yes. Okay, so I have opened a little poll just out of curiosity, and I also see some other questions. On the chat, so let me address these unless there are other questions that Suji is giving here from a guest. We're heavily using SQL and Hive. Is Spark applicable to us? Here the answer is that I don't like to say such things, but it depends. Now, SQL and Hive are all implemented in Spark as well. So if you're using, first of all, SQL by itself, then it may be that you're using a schema that's too complex and won't fit either Hive or Spark. That's probably not your situation because you're already using Hive. So then the next question is, would you want to use Spark? The answer is you should at least look at it for this reason. Spark has Spark SQL. That is pretty much the same as Hive. The only question is performance, and it depends upon how exactly you implemented your Hive. Is it Hortonworks or is it Cloudera? If it is Hortonworks, is it running on Tez or no? Hortonworks has a benchmark that runs, as they claim, faster than Spark. Spark in turn has a benchmark which runs faster than everybody. So it depends upon who you ask. But the reason you would want to look at Spark, at least look at it, is because it does all of that Hive does, but it does much more as well. So depends. If you don't want this much more, then you don't need it. But if you're interested in what else, then Spark for you starts where Hive ends. Another question. Guys, you're asking just very nice questions. Next question is from Karilda. I've done some classes that use Python notebooks. Please comment on the use of notebooks. The notebooks are extremely popular. That's a very good way to train because it usually works. But it is also actually a very good way to do production. We had some projects where we were doing notebooks. I think it's IPython. And it's a very good way to package. So yes, it's a good thing. And if you are comfortable with this, just continue doing your Python notebooks. It's not the wrong approach. It's great and it's used in many companies. A question from Ashish. How is enterprise, not IT companies, adoption of machine learning? Can you please give some examples? Well, if you say like a big communications company like Comcast, for example, if you say that they are IT, then I'll take them out. But if you say that they're enterprise, then huge. We taught classes there, and these guys, I mean, not specifically at Comcast, but at telecommunications companies, and these guys are all about machine learning. Or let's say you're a network provider. Again, you need to do well, network providers under IT, all right. well, let's say healthcare, right? Healthcare is definitely a lot about machine learning. And one example that I cited had to do with patient classification. But from there on, you go to anywhere. Lots of people have big data, and that started showing up lately because once they know what they can do with the data, they stop throwing it away. They used to just discard it. But now you find it everywhere. So let me think of healthcare. I've seen a lot. In competing products for competing companies, they all use machine learning. In legal, I don't know how much not IT it is, but definitely it's all the rage in legal. And then, let's say, engineering for jet engineering, like Boeing, that they definitely use machine learning and so on. So I would say yes. People start with machine learning, not necessarily with deep learning, but with that they go pretty far. Great, so I've been told that we have just a few more minutes and I think there are no more big questions. So guys, thank you very much. I really appreciate your coming. I kind of heard you. I know there was no sound, but from the questions I understood that you were really interested. So thank you very much for coming. The recording will be posted later on. And yes, just as Suji mentioned, email us with questions. And see you next time for some other interesting and exciting topic. Thank you very much.
Good job, Mark, and thank you so much, everybody.